to week 4, Steel's out, okay? So we're gonna go over beam flexural theory, and then we'll go over everything like leading up to being able to do flexural design. So flexural design, by the way, is another way of just saying bending moment design, right? Okay, so let's look at a picture because it'll make it way more obvious. So when you have a beam, right, there's gonna be gravity loads on it, and it's gonna put your beam into bending. That's like the primary purpose of the beam. And then the beam's gonna deform in a certain shape, right? And engineers approximate it to this shape, right? And what you can see here is strain. So if you've done concrete already, you might already be familiar with this, but if you've only done solid mechanics, you might not fully have digested what this means, right? But do you see how you kind of have this linear shape for strain? So, you know, I'm just gonna ask you guys, right? What is a good way to describe strain? Like, what is strain? If you have it.
Opposite of stress.
Opposite of stress.
Stress.
I think there's another way to put it, maybe. Like so if stresses are to do with forces, what are strains to do with?
Per unit length or something?
Deformation.
Yeah, deformation. Yeah, that's the way to put it. It's just how much how much something's deformed, pretty much, right? And so there's actually 2 forms of strain. There's tension and compression, right? So if you can be stretching something, so pulling it apart means you're putting it into a tensile strain, and you can be pushing it together, which means you're putting it into compressive strain, right? So when I bend the beam like this, which is the shape that's gonna go into like under gravity loading, right? Is the top gonna be in tension or compression? And what about the bottom?
The top is going to be in tension and the bottom is going to be in compression. I mean,
Other way.
Yeah,
On the screen.
that's what I said.
Yeah.
I mean the other way. I mean that's
But
what
the bottom has to be in tension, right? It's okay. So wait. Before the recording, we were talking about a cake, right? A cake is made up of like little particles of fucking flour and all that stuff, right? If you bend the cake, right, the bottom's gonna be in tension. What's gonna happen to the cake?
It's going to rip the cake.
Exactly. It will do this. So that's what happens for concrete.
Oh my
Right.
god.
Do you remember? Because you've done concrete, right? That's kind of how concrete behaves. But steel's different. Do you remember why?
Because steel is stronger in tension.
That's true. It is stronger in tension, but what does it do in
Fracture.
tension? Or it fractures if there's not enough area.
Yields.
It yields. Exactly. Yeah, to give you a you got that there. So the bottom's kind of yielding, right? Kind of doing this. What's the top doing?
Like,
It's compressing, right?
yeah.
It's kind of crushing, right?
Like folding away.
Kind of. So it kind of does this, right? That's like kind of pushing together marks and imagine like wrinkles kind of thing, right?
That's
But do you see how there's different behavior at the top and the bottom for steel? That's going to lead to a very interesting phenomenon. I'm going to show you guys this. It's going to fucking blow your mind because it blew my mind, right?
Wait, let me.
You're going to learn, right? So, okay. Rewinding to compression, right? In compression, we have our major axis and our minor axis, right? So, do you remember the major and minor axis? Okay, basically, the major axis bending is kind of this way. So if I try to put loads on it, right, like down like this, that's going to be stronger direction, that's going to be the weaker direction. So that's the minor axis, right? Okay, so and then what happens is, for this shape, we kind of get this buckling, Euler buckling effect, right? Remember, that's in compression. Because what I'm doing is I'm pushing the column or whatever. I'm pushing the column, it's going to buckle against the minor axis. But then, here's the thing. You're on recording. Lock in. Stop viewing. Okay, bring that here. Okay, so what I'm gonna do, right, because I don't want to break this stick thing that I have, right? If I put my arms like this, right, I'm trying to like twist it. I'm kind of racking the stick, right? So it's gonna pretend like it's bending. Okay. So there's a very interesting thing that happens when I do that. Do you see what's going on? Do you see how the shape is like in the middle? It's like kind of bowing out.
No, I can't see.
Right.
Oh, there's like at the top, it's like bending.
Kind of. The top one's a buckle, right?
Can you show us like
What's the bottom doing?
bending, staying still?
Maybe better
Oh,
on that angle.
the bottom is
let's
straight, but the
focus.
top
Okay,
is...
do it again from straight. Let me wait.
Show us
Wait.
like the top angle. Yeah.
Wait, okay, it's focused. Go.
So now I'm racking it. Oh,
Oh,
it's kind of snapping. Do you see what's happening?
yeah.
So what's happening in the top flange
It's buckling,
is it's in tension or compression.
compression.
Exactly. So the compressive thing that we learned, where compression causes buckling, still happens, but only at the top particle. And the top fibers, right? But the bottom, what's happening? What happens when you pull on a rope?
Go in tension.
It straightens out. Right? So, let me draw this out. It's a very interesting phenomenon. So if this is your normal shape for your I-beam, right? At the mid-span, right? So if we're deforming it like that, right? We're pushing it down. Oh, sorry, that's not a very good way to put it. We're adding like a UDL to it, right? And then it causes the whole thing to bend like that. You can stop recording, by the way. What happens is that, firstly, we're looking at the I-beam like side on like that, but we're cutting it here. So that's the section that we're looking at, right? Does that make sense so far? So what happens is this shape goes down, right? That's obvious. That's just like the deflection downwards, right? So it's moving down. But then what also happens is that we got this, correct? We got this twist. Do you see what I did earlier?
Wait, so that's the... Oh, okay, yeah.
And then we also, so there was some amount of lateral deflection and there was some amount of twist.
Out of plane.
Yes, it wants to laterally deflect out of plane.
This is how all the twists
No, shut up. But then it's twisting as well. So why do you reckon that is?
Feels like tension versus compression.
So the top is in tension, so it wants to buckle out, right?
Isn't the bottom in tension?
Oh, sorry.
Oh!
The top is in compression, right? So it wants to buckle because that's what we know about the compressive thing, and it wants to buckle against about the minor axis, right? Which means it wants to go sideways. But the bottom is in tension, which means it wants to straighten out. So the bottom wants to straighten out, and the top wants to go out. So now you get this twist. So this is called lateral-torsional buckling. So before we had Euler buckling, and now we have lateral-torsional buckling. But that's not this course. But yeah, do you guys have any questions about lateral-torsional buckling? That's kind of where we're going to go. But what we're going to do is we're going to do the members, the section capacity first, before we do the member capacity. Everything I just talked about is to do with the member capacity. Because you know how when we were doing compression, we had NS and NC? That's the equivalent. So we had the section capacity and then we had the member capacity.
The section capacity is like local and member
Yep.
capacity is global.
Exactly. But we have a different mode of global buckling because the global buckling before was Euler buckling, which was this. Now we have lateral torsional buckling as the new.
Laterally
Do
torsional.
we need to check for Euler buckling and...
No.
Why? Will the question tell you which one is doing?
Oh. For columns. So the last topic of this course is columns. And you know how I said columns don't columns do the Euler buckling because they have compressive loads. But think about it, columns have moment and compression. So you have to check for both in the last topic of this course.
Didn't we already do columns?
No.
We did frames.
We haven't formally done columns. You guys did trusses. You did trusses.
And frames.
Oh, yeah, the gamma method? The gamma method is a part of the last topic in this course, which is column design, basically. It's beam columns.
Beam column.
Yeah.
That's crazy.
It's everything. Like, the last topic in this course is like fucking everything summarized.
That's awesome.
Except tension, maybe. And maybe no shear in it either. But yeah, anyway.
Oh shit.
Okay. Okay, here's the thing, right? So we know the material curve for steel looks like this, right?
It's on the... It like... the stress doesn't go more, it just stays still.
Oh yeah, that's pretty much it. Yeah, so that's the yield stress. That's the
Oh,
strain, right? And so it
But
plateaus.
why does strain increase if stress is the same?
Oh, so strain is like the x-axis, right? So it like keeps going. So we're saying like, what happens if we keep pulling? Like on a machine,
It will continue to pull.
but it won't.
But
It won't do any more
it's
stress
flipped.
response.
You know how the independent variable is usually on the x?
No. It still is on the x.
Well, we're changing the stress, so really.
No. We're changing the strain. In an apparatus, you constantly change the strain and see the stress response.
So it's stretching, but the rest is not changing.
Yes.
But it's stress of what?
The
you
materials
don't
response.
have
The
to-
materials response.
So you don't have to.
The resistance it gives for the strain will plateau out. It won't keep giving more and more resistance in like when you have the like
Well, what happens
hydraulic
until it
pull
like
apart.
becomes broken?
So what happens in the apparatus, right? So you have let's just say I don't know what shape it would be. Let's just pretend it's like that, right? And it's being pulled apart. Let's say in tension, because tension's easier to test for, right? So what happens is it keeps pulling and it gives a linear amount of increased resistance as you strain it. But then once it reaches yielding, what happens is it starts doing this kind of like cheese melt thing. As you keep increasing the strain, and the rate at which it like kind of melts like cheese will make sure that the resistance is like this kind of plateaued amount.
Yeah.
Does that make sense?
Yeah, it makes sense. But then what
Yeah.
happens when the cheese melt breaks?
Oh, then
It
it
just
snaps here. Yeah, it increases a bit more. The resistance increases a bit more,
Really?
and then it will just eventually snap. So then you get this
And
kind of
then
like
it
brittle
becomes
break
zero.
at the very end.
So the graph will go.
Yeah, it could drop. Yeah, it's like the data is like incoherent once it snaps.
That's so crazy.
Okay, but that's like how steel behaves, right?
Crazy.
So, basically, what this means as we increase this like kind of slope thing, so it might start at like 0, and then it goes like that, and then it goes like that, and it goes like that. So what are we doing to it physically? The strain.
Can you say that again?
So as you keep straining it, right, it means that we're adding more of that like kind of racking pressure, right? That's what we're doing when we're straining it more, right? So I'm increasing the amount of displacement I'm doing, right? And then originally it starts with this elastic response, and then here it's reached its yield limit on the edges, right?
Oh, on the edges?
So just the edges have yielded. So what, like, I've got a question for you.
Oh,
So if I have tension, it will yield at every point along the depth at once, right? Do you know why that is?
Because it's like even force.
Exactly, it's evenly being strained. So if I was talking about pure tension or pure compression, the graph looks like this, because I'm applying an even amount of strain throughout the entire depth, right? So it's like a rectangle.
So if you're looking at it like, okay, yeah.
But then if I talk about it in terms of that, it means I'm applying an uneven amount of strain.
So you're like bending it.
Exactly, I'm bending it, because the top's in compression, the bottom's in tension, right? In normal case bending. But then, so the very top and bottom fibers will yield at the same time if it's symmetrical, right? But it's a different type of yield, because the top will yield in a compressive way, and the bottom will yield in a tensile way. Does that make sense?
Yes.
Okay. Do you actually get it? Or...
Yeah.
Okay. And as you keep going, more of it's going to be yielding. So everything that's become like a rectangle has now yielded.
Yeah.
So it's like the top fibers and then a bit under it, and the bottom fibers and a bit above it. They've all yielded now. And so once the entire thing has yielded, because we've bent it so much, this is another critical point. So that point 2 and point 4 is called the first yield bending, and the fourth point is a plastic bending. Does that make sense?
So it's like cheesing on the bottom and like becoming a book on the top.
Oh, I kind of know what you mean.
She's making
Yeah, she's saying facts. So for the first yield bending, yes, the very outer fibers is just what you said.
It's plastically deformed.
So there's like one layer
No, it's just
of cheese.
the first yield bending just means like as soon as it's barely reached yield, as in like just
So
those
it's not
fibers.
Plastic.
So the plastic point is when the entire thing
Is plastic.
has yielded, including the middle fibers, like near the neutral axis.
But then doesn't that mean like
The entire thing has become cheese or whatever, I guess.
So the bottom bits are already like cheesing a lot, and then the middle bits just become a little bit of cheese.
That's in this stage that I described.
So when is it plastic? At 4.
The entire thing has to be yielded for it to be considered
To
plastic.
start being plastic. Oh.
Or that's like the definition, right?
So you could have one fiber and it.
Then it's called first yield.
But then
It's
it
called
does
plastic.
back. No, one fiber not yielded.
Oh, so
And
if
the
you
whole
go
thing will
to
turn back to
no, it's a point of no return. So like if you go to 3
Yeah.
and some of it's yielded and some of
Yeah.
it hasn't,
Then some of it's
and you unload it,
Uh,
then some of it will be plastic and some of it won't be. Right? It's just the outer layers have become plastic, right?
wow.
Wait, what does it mean if something is plastic? Like, what's the property of it being plastic? Like,
It's reached yielding. So
Does
so
it mean-
it's this is the plastic region, right?
Yeah.
It's reached yielding.
And
But
does that mean it's like weaker? Or...
But for this definition of plastic, so plastic bending means the entire thing has to become plasticized. Sorry, and wait.
But what does plasticized mean? Like, is it weaker or like you can't use it anymore?
Oh, think of it like this, right? So an elastic band. Pretend I have an elastic band on me, like hairband or something. I'm stretching it, and I let go, and it becomes the exact same shape that it was. That's elastic. That's an elastic band, right?
Yeah.
Fucking think about it, right? No, I'm kidding.
The plastic band.
But plastic.
Piece of plastic bag.
No, but the best thing, like, the best way to imagine like the definition of plastic by like the material science definition is Play-Doh. It's literally Play-Doh. So if I mold Play-Doh, it stays in that shape. The entire thing's fucking plastic, right? So imagine when I say like this beam has become plastic, it's become like Play-Doh.
Oh my god.
It's like permanently deformed, and
Oh
any
shit.
change you do to it will be permanent.
Oh my god. That's
And
so
it just
crazy.
crumbles like plastic.
Huh?
Like Play-Doh.
No, that's cap. But yeah, does that make sense? Yeah.
Yeah, that's so insane.
Okay, good.
That's so crazy.
Okay, next thing to understand is section classification. So what do you notice immediately about these diagrams?
It's like becoming thicker and then thinner.
So we call it compact is the thickest one, and then non-compact is the middle, and slender is the thinnest, right? But what do you notice about the correlation between compactness or slenderness versus, I wish this quality was better, versus it's called the section plasticity slenderness limit and the section yield slenderness limit. So it's to do with what we just talked about, right?
The ratio of the thickness of the flange and the web are the same.
No, it's more about what I just talked about earlier, right? First yield bending, plastic bending. Okay, think about it. Like, what's the best case scenario to utilize your steel material? Like, do you want it to only behave elastically and then break and then snap, or do you want it to reach plasticity and then snap?
The second one.
Yeah.
The second one, right? And what about, like, from your understanding from the compression design, do you think compact or slender sections are more ideal?
Compact.
Because they'll be less likely to break elastically, right?
Yeah.
That's what this is saying. What happens is, if you have a slender section, it might not even reach yield at all before it breaks. So it'll be like an elastic band that just snaps. That's how it'll behave.
Oh my god.
But in
Oh
bending,
my
think about it.
goodness.
That's what a slender section does, right? But then, on the complete other end, we have a compact section, which is the best case scenario because it's going to fully plasticize. The whole thing's going to become like Play-Doh in bending before it breaks. That's what it's saying. And non-compact is somewhere in between. Does that make sense?
Yeah.
Yes.
Meaning, like, for example, slender, it's more likely to like fast fracture.
Pretty much the equivalent. Because
Okay.
there's a brittle failure mode. Brittle just means it doesn't really give before, like it's going to break suddenly. That's what brittle means. Yeah. So slender will break suddenly. Right.
Shoo!
Okay. And then, shut up. All right. And then, so now we have another thing to consider. Elastic section modulus. Have you guys seen this before? Z? Sorry, I know it's fucking blurry as
No.
fuck, but
Z.
Have you seen this equation before? M equals Z times strength? Maybe not.
Moment equals force times distance.
No. It's not quite that. So basically,
Oh, like depth.
you've definitely seen it, just in another form
Like
before.
depth. Like
Kind
soil
of.
mechanics.
No.
Oh.
Z is not like that's lowercase z. That's lowercase z is elevation, right? It's
Yeah.
not that. Basically, you know this equation. He's definitely seen this from solid mechanics before, right? It's a bending equation, so it's like, it's basically like if your strain's like that. No, it's actually it's like if your stress is like that, it's elastic, right? And then y is the depth. So you have the right idea. It's just denoted by y. So imagine like a linear algebra. Y just means how far down you've gone in your graph, right? And you're trying to plot this. You're trying to plot stress. And so how far down you've gone is going to be, yeah, you're going to be able to graph the stress basically. And this moment is whatever moment you have along your beam. Say it's in the middle. And your I is your second moment of area. Okay, I'm kind of fucking losing you guys, I think. Basically, one sec. Basically, sorry, let me write that again. So this is just maybe for a second, accept that this is a formula from solid mechanics, right?
I'm good at accepting.
M over Z is equivalent, right? Because Z, this elastic section modulus, is I over Y hat. Okay, so why is that the case? It doesn't really matter. The point is, this is how you graph the stress curve if it's a straight line, if it's elastic, right? So if we go back to here, right, you're allowed to use that equation in stage 1 and 2 because it's a perfectly straight line that you're graphing, right? Does that make sense? But then you're not able to use it at 3 and 4. That's
Right?
it.
Like once you get there, you can just figure out how straight the line is.
Yeah, we did some concrete, didn't we?
No, because basically it's graphing this diagonal line. It's graphing that diagonal line. Yeah.
Okay.
We do this in concrete for unreinforced concrete.
Yeah.
Because once you get reinforced concrete, the material curve for concrete looks like this. A parabola, right?
No.
For the compressive side.
Okay.
So you can't use that equation anymore. So it's only for unreinforced concrete, and the moment it cracks, that's called the cracking moment. You can't use that formula anymore, right?
So that formula it's like equivalent to saying y equals mx plus b.
Kind of.
Okay.
No. It's okay. You know what the best way to think about this is? You know how I always say like, what's the stress formula?
Area. Force over area.
Force over area.
Oh no, I know this.
But how is that possible? How can it be force over area and m over z?
Because
It's gonna blow your mind.
moment is force times distance and
No.
area times. Okay.
Too much. You're cooking too hard.
I'm sorry.
Think about it like this, right? So if I have my stick again and I'm pushing, that's an axial force, right? I'm doing compression. So I can compute the stress by doing force over area, right? Is that the case in bending? Why not? Because the stress isn't even throughout the cross section. So you can only apply this formula at the top if our stress looks like this, right? Because that value for stress is your force over area. It's a single number. But if it's as soon as it's diagonal, you need to use this formula.
Oh my days.
So that's fine. Wait, okay, continue.
But there's analogies, right? Like it's you know, force can be kind of like similar to moment to some degree, right? And area can be kind of thought as your elastic section modulus. So whenever you see elastic section modulus, just think of it like the bending area almost. It's harder to kind of fully understand because the units are mm to the power of 3, but this one's mm to the power of 2. That's just like a mathematical quirk.
Yeah, so isn't it like F times D and then A times D?
You can think of it like that maybe, but like I feel like it's going to be more confusing. But your Z is just you know how like on one steel, like the questions so far have just been like, what's the minimum area we need to satisfy this compressive whatever. Here we're gonna do what's the minimum Z we need.
Okay.
That's with an asterisk in terms of I've oversimplified it. We're gonna need a ZE, which I'll explain later. Does that make sense? That's a function of Z. Z shows you how, like, it's the equivalent of area but for bending. That's the simplest way to put it. Okay. Got it, Lucky? But you're a solid mechanics teacher. Surely you've seen this equation before.
Yeah, I understand.
Oh, okay. Anyway, but let's go on to that later. Similarly for plastic section modulus, now the stress curve looks like this.
Uh-oh.
So now we can't use that formula anymore. Guess how we do it?
Wait, I thought you can't use it for push 3 as well.
You can't do it for 3 either, but we don't never need to calculate 3. We only need to calculate 2 and 4.
Fine.
You do it the exact same way you do it in concrete.
Oh!
You take the sum of the moments about the neutral axis. So you pretend that you turn these stresses into like these stress blocks into forces, and you do sum of the moments about the neutral axis.
And you have to take into account the depth.
Yes.
Jeeves.
Okay, that's it, right?
Done. Home time.
Lateral-torsional buckling. So we've talked about this a little bit, right?
Yeah.
But these are the definitions in the code. I've explained lateral-torsional buckling conceptually, but do you remember how I said for compression that you can restrain, like if I, so if I'm pushing down on this like in a compressive way and I restrain it in the minor axis, it does two S's. Oh, sorry, it does an S shape. So for anyone in the video, it does that if I restrain it in the middle, basically, right? Rather than fully buckling out. So this is for compression and Euler buckling, right? So now for there's a similar concept for bending. I can restrain I can restrain this action, right? The racking.
Yeah.
But what am I restraining? Where do I need to restrain it?
In
Because before I could just restrain in the middle and it makes sense, right? Like, where do I need to restrain it? Do you think?
The top?
Yeah, why?
top middle.
Because the top is like
Maximum compression.
bending.
It's buckling.
Uh-oh.
But, you're completely right though. You have to essentially restrain the part that's going to laterally torsionally buckle. And it's a compressive flange most of the time. Except-
Flange.
Oh, sorry. The reason why we're talking about flanges is because most of the time we care about this is for I-beams, right? And when we're talking about flanges, we have the top flange and the bottom flange. The top flange in the normal bending cases is going to be in compression. The bottom is going to be in tension.
Mm-hmm.
So we have to restrain the top flange. So we have to have something stopping this from moving in and out of the page and twisting and stuff like that, right? But what about for a cantilever? Right, so a cantilever is like a beam that looks like that. Which way does it deform? So if I were to put like pressure on it, so think of a diving board or something.
Oh, it's the other way.
Yeah. So
Compression's on the bottom.
compression is going to be in the bottom, and tension is going to be at the top now.
Uh-huh.
But there's a caveat, because for some reason, if you look at test videos of lateral torsional buckling, if you cantilever, it tends to fall out from the top. It tends to laterally torsional buckle from the tension side,
What?
which makes almost no fucking sense.
Can we watch a video on it?
I can't be fucked to pull one up, but just trust me, bro.
Trust me, bro.
Look at a video of it, cantilever lateral torsional buckling, and it tends to fall out from the top like that. So the tension side, even though it's in tension, it's fucking laterally torsionally buckles. Happens every single time for whatever fucking like solid mechanics reason. So let's just do a quick fucking thing, right? If we have a continuous beam, right, which just means like that part's simply supported, and then these two parts cantilever out, right? Do you know what the bending moment diagram looks like? That? Did you say?
Yeah.
Are you following Sue?
Yes.
Sorry, I should probably draw it like that. I think
Is
it's.
that why the Harbour Bridge is made like that?
I think so.
Yeah.
I think there's some reason to do with. I don't know. I don't do bridging engineering.
Light Bridge.
Yeah.
Or Golden Gate Bridge.
I think there's a different reason though,
Oh.
because they just have tension cables, and then it's to do with like how tension cables need sagging in order to
This one
fully.
has a cool shape.
Yeah. Yeah.
Yeah.
Okay. Anyway. Okay. Focus. So this is bending moment diagram, right?
A bridge.
So this is positive bending. This is negative bending. That's positive, right? Oh, sorry. Yeah, fuck. I'm fucking tripping balls. Out the way. That's positive. That's negative, right? So basically, it's sagging in the middle, right?
Yeah.
So you tell me, where's the compressive flange going to be? So imagine the entire thing's a universal beam. Like that. Okay, in the middle. Where's in the why?
Because it's in compression.
So we call that. Let's just draw it like that. We call the top the critical flange. So now when I write C, that means critical. Critical means the worst one, right? Okay. What about right here? Sorry, in this region. Let's highlight it in purple. What about in that region?
Bottom.
Why?
Because it's sagging over the point.
It's in compression.
Yeah.
Because compression is the critical flange, and
Yeah,
it's in compression
sagging
over.
the point.
Okay, but what about for the cantilever span?
Then it's back to the top.
Exactly.
Because of the rule.
So these points are the points that need to be restrained in order for what's the word?
Laterally torsionally buckling.
So sorry, in order for you to like reduce your LE basically.
Oh.
We have remember LE is like your effective length.
Yes.
So if your critical flange is not restrained, then you can't reduce your LE basically.
Yes.
And you're gonna see all these details and stuff in like workshop questions and everything, and it's just to do with various restraints, right? So let's talk about that. There's fully restrained, partially restrained, and unrestrained. Unrestrained is the easiest to understand. It's basically a cantilever end is unrestrained. That means there's nothing restraining it, basically, right? Fully restrained. You know what? We'll go back to that. Oh, I just demonstrated the critical flange thing there. Here we go. Fully restrained means the critical flange is restrained, right?
Mm-hmm.
Oh, you can't fucking see these details because it's so blurry.
Just zoom it in a little.
Okay, but C just means critical flange, right? So let's see a good example. That's a good example. So let's say this one. No. Yeah, let's say this one. You know what? Fuck, it's easier. These aren't actually very good diagrams. It's easier to see in questions. We'll cover it next week. I just want to tell you guys about the rough concepts first. Okay, let's look at flexural design, the equations, right? It's very similar to compression, basically. Right? We have MS and MB. Remember, in compression, it was NS and NC.
Ooh. Got it.
But it's just member design. It's member capacity. But C, I think, stands for compression, like axial compression, and then B is like bending. I don't fucking know how they came up with these terms, right? Hold on.
Buckling.
But they're both buckling. One's Euler buckling and the other's, you know what I mean, lateral-torsional buckling. Here's some drawings, but hopefully it just re-emphasizes the point. But this is for section buckling, which we haven't even really talked about too much. We've mainly talked about lateral torsional buckling.
Oh
So
my
it can it can buckle in section, but we have to calculate the section capacity first, just like for compression,
That's awesome.
and then we have to go to the lateral torsional buckling.
Okay.
Okay. Now we have this thing, effective section modulus,
Z, that's what we've been looking at.
but it's ZE. That's why you have to calculate Z and S, because effective means it could be anywhere between Z and S. And actually, it can be less than Z for what we could tolerate, right? This is ZE. So if ZE is here, right, then it's non-compact. If ZE is here, it's compact. If ZE is here or less, it's slender. So ZE is like some value which fluctuates between Z and S.
So did we actually need to find Z and S earlier?
Yeah.
We have to.
Like I haven't even shown you how to calculate ZE, but it's in between those numbers or slightly lower, if it's slender, right?
Oh my goodness.
But the other thing is we don't have to calculate S if we have a slender section, because it's only dependent on the variable Z. Because if it's all the way all the left, yeah, we don't care about what S
So
is.
the solution's monotonic.
Do you think Z or S is bigger?
S.
Yeah, because it's like a higher capacity. It's like the same thing as like area, right? But for bending. But remember, it's
area is
yeah,
bigger.
yeah. You kind of get the idea, like the gist of where this is
Well,
going, right?
just do that because you wrote S on the right.
Oh yeah. But you can think of it almost like a timeline, kind of like a number line or whatever, right? Like that. Okay.
What's S?
Yeah.
S is the section member capacity.
No. S is the plastic section modulus. Z was the elastic section modulus. S is the plastic. And that remember that's when you reach full plastic yield.
Which is a constant.
Yes.
S is a constant.
Yes. It's to do with the geometric properties.
So what's the units of Z and S?
Mm cubed.
Oh, okay.
Remember, that's just gonna trip you out if you think about it too hard.
Okay.
So that's from one steel.
Unless it's a custom shape.
Oh.
So ZE is actually given in one steel. You don't have to do any of these S and Z calcs if you do a one steel shape. Problem is your assignment, I guarantee you your assignment is a fucking custom shape. But it takes forever to do this, which is why he won't make you do it in exam, fingers crossed. Unless you're me in 2023. And you fucking made everyone do a beam column custom section. Anyway, I digress.
Crazy.
But most of the time,
So in the formula,
Mhm.
the first yield moment or the plastic moment, we calculate that
if it's a custom section, you need to, yeah.
the normal way.
What's the normal way?
It's like force times area.
The plastic or the...
Either. The plastic one.
No, the plastic one, you have to do some of the moments, like the concrete way.
Yeah, the concrete way, that's what I mean.
That's not F over A though.
Isn't it force times distance? Like
No.
the cumulative force
No.
times the distance?
You have to take this moment couple.
Yeah, that's force times distance.
Kind of. But it gets more complicated if you have an unsymmetrical shape and stuff like that, yeah.
Okay.
Yeah.
Okay, and then Fy is just the normal yield.
Yes.
Ah.
Fy is basically in every part of this course.
Ah.
Yeah. We only use Fu for tension. For fast fraction, right?
Okay.
Because steel's material curve, only one number fucking matters, right? It's Fy, right? Because there's in tension and compression.
Yeah.
And bending, because it's both, right?
Yeah.
Okay. So, lambda denotes slenderness, right? Are you guys alright to keep going? Or...
Yeah.
Okay.
Yeah.
So, we have to determine lambda S, lambda SP, and lambda SY. So the S there stands for section.
Mm-hmm.
So we need to find the slenderness of the section. We need to find the plasticity of the section, and we have to find the plastic limit and the yield limit of the section. But guess what? We have to check every element and find the most critical element to find the sections one. So when I talk about an element, what I'm talking about is a fucking you know, imagine these are made of 3 plates, right? This like beam. There's 3 elements, bro. You find the most critical element to find this entire section's limit. Do you get what I'm saying? Because it's the one that's most susceptible to locally buckle. Remember, locally buckle means like this fucking flange or something fucks up. Yeah, exactly. Right? So we have to find the slenderness of each element, which is that formula there, right? We have to note down what the yield limit is for every element, right? Which we can find from the table. But the thing is, this table, it should look a little bit similar to, because you guys did the assignment, right, for compression. But parts of it are different. I'll tell you why, right? Because it's almost the exact same thing. It uses some of the exact same values, right? But you have to be able to interpret what some of this yapping is in the description, right? So I'm going to highlight it. What I've highlighted here in purple, you can't really see it because it's fucking lagging, but it says uniform compression. What I've highlighted. What does that mean to you? You know, in terms of the stress diagram.
You assume it's the worst. You draw it as a straight line.
Uniform compression is like this shape that I just drew. I'm not sure if you can see that. This rectangle thing, right?
The force is constant.
But we're talking about an element, right? So if we look at an I-beam and we just care about the top flange, right?
Yeah.
Is the stress uniform? Is compression uniform?
No. But it's telling us to consider it as
Pretty much. It's like this trapezoid that's nearly uniform.
But it just says make it a rectangle.
Yeah. Okay, but what about the web? Is that uniform?
Also no.
But less so now, right? There's no way in hell you can call that a uniform compression.
But it's saying call it uniform?
No. How would you describe that?
Rectangular.
The stress thing? This blue one? Sorry, we're talking about the web now.
Triangular.
They call it maximum compression at one edge and tension at the other.
Yeah, I can see that.
Exactly, right?
That is what it says.
And that's what it is, right? Because on one side you have tension and the other side you have compression. That's how you have to interpret the table.
Yeah.
Right. Now there's another thing that says supported edge and unsupported edge. So what does that mean? Here's an example. You have a sideways I-beam or like a column, for example. Do you see how one side's supported and the other's not?
So there's a big difference.
Yeah, because the supported side is zero stress, essentially. And then the unsupported side is in compression.
Maximum stress.
Yeah, basically. That's what I was trying to say, right? And why does it say compression and not tension, do you think?
Because tension is the buckling.
Exactly. It's all about buckling, right? So we just care about the compression side, like the compression part of it, right?
For real.
Yeah. Okay, and then here we have a square hollow section. And the description is compression at one edge and tension at the other. Right. And that's what this one is here. It hasn't popped up yet. Yeah. Because for this like web element.
What's the difference between the first one and the third one?
Longitudinal edges supported. One or both.
Oh, one or both. Oh, I see.
Yeah. So because there's 2 supports on this one.
Yeah.
So those are all the cases you're going to get. And then circular hollow sections have their own part. Okay, I've got a question for you. I'm not sure. It's kind of annoying because you can't really see the numbers very well. But do you see how it increases, kind of, like the numbers kind of increase as you go down the table, right?
Yep.
Okay, so is being is having a higher slenderness good or bad? Bad for the capacity, right?
Yeah.
Okay, but what about having a higher slenderness limit before you reach yielding or plasticity?
That's good.
Why is it good?
Because it can take on more stress before it.
Exactly. It can be compact or it can be non-compact before it reaches slender, like before it's considered slender or some shit, right?
Yeah.
Okay, so with that in mind, How come the circular hollow sections are better? And to some degree the square ones, which are like these two.
Higher limit. Higher plasticity limit or yield limit, is that what you're saying?
Yeah.
Why do they have a higher limit?
Yeah, as a general kind of thing.
Because they're supported.
Yeah, they're supported from more like edges, I guess you can say. There's not really, for a circular hollow section, there's basically not an unsupported edge,
Yeah.
right? That's locally, but let's just, sorry, I know I'm digressing a lot, but let's think about lateral torsional buckling. So do you remember that thing we were talking about, how for the entire beam, if you put it into bending, right? Imagine this is a square hollow section, or let's just say circular hollow section, so it looks like that, right? Lateral torsional buckling, remember, means twist and deflection sideways.
Oh, it's easy for this guy to twist.
You sure?
No, it's slippery.
No, what about deflection first? So does it have a minor axis?
No.
Because it's a circle, right? So its major and minor is about the same. So firstly, it doesn't really have a minor axis.
Yeah.
So it's harder to laterally deflect.
Yeah.
Okay, the next thing is twist. Basically, do you know how the warping constant or twist, like, do you know how that's calculated roughly?
No.
It's about how much meat there is in the next part that...
This looks really easy to twist.
It's actually really hard. Imagine twisting a fucking pipe.
What?
Like, it's gonna be really hard. There's a lot of meat in the way of like
easy to
the
twist?
a beam, a UB. This is incredible. Like, actually no, just like a
rectangle.
like a plate. A plate is incredibly easy to twist, right?
Okay.
If like, oh, I twisted this, it's gonna fucking break instantly, right?
Right.
It's got the worst twist.
Right.
Yeah, and then an I-beam's pretty similar to that. So that's actually got horrible torsional strength.
Ah, so
That's why we have to do lateral torsional buckling checks for
Ah.
I-beams, because they're actually really, really bad in twist.
So that's how we do them in circles.
But at work, we basically consider circular hollow sections and square hollow sections as they cannot laterally torsionally buckle.
So in
the-
the assignment,
The MS is effectively the MB.
so if I pick
like-
a circular section in the assignment, then I'm good.
No, but
Let's
you know this assignment, if it's going to be similar to last year, is not up to you. It's
Okay.
you have to make a custom plate. Sorry, a 3-plate section that looks like an I-beam, and the size is dependent on your ZID.
Right, so in the exam, I can just pick a circular section.
I mean, there's still checks for it, but I guarantee you the MB will be much higher than the MS. You still have to follow through all this stuff. Yeah. But MB will be higher than MS, but it can't be higher, so you have to set it down to MS. Yeah. They essentially cannot laterally torsionally buckle.
Okay.
They're going to fail in bending, like normal bending capacity
Okay.
before lateral torsional buckling occurs, you know? Okay. Anyway, sorry. The next step is you have to calculate all the elements, slenderness to slenderness yield ratio, and the max one is going to govern. The worst one's going to govern, right?
Max. Yep.
Okay. Now we put a pause on that because we have to determine Z and S.
Yeah.
Because we're finding ZE, right?
Yeah.
So now we have to do all this shit. And Z, simple formula. Z is just IX over Y hat, right?
Yeah.
And to find IX, you got to do all that shit. You got to this for rectangles, this for circular hollow sections, all that, right? But and you can also do it this way, but I wouldn't recommend it because it's much easier just to plug it into a formula because it's all elastic, right? So your stress curves following this really nice.
So you said it only works for uniform materials.
Oh yeah, that's why we can't do it in concrete.
Oh, not uniform shapes, uniform materials.
Oh, we can't do it. Yeah, but steel we're considering one material. But for reinforced concrete, it's multi-material.
Yeah.
So this doesn't work anymore.
But it does work in this course.
Yes. So don't do method 2 basically. I've just listed a few information. But for S, you do have to do it that way.
What?
Because you can't use that formula. Yeah.
Find MP the no by foot. Okay.
Okay, so now this is a reduced Z and S if there's holes. To be honest, they skip this step most of the time. Don't worry about it. Unless like for your assignment, if they're fussy about it in like one of the assumptions, then do it. It's basically saying reduce your section moduluses if there's too many holes in them, because then it's the same thing as like area and effective area basically, but for Z and S.
Makes sense.
And then effective section modulus. So we finally reached it. It depends on if it's compact, non-compact, or slender. Okay, the formula to get it.
Oh, okay.
So that's why we had to, determine whether our
ZE
sections.
is easy, bro. That was nice and
But the compact one's easy.
Yeah.
But like non-compact and slender's even more aids.
But haven't you already found these values in the step above?
Yeah.
So it's chilling.
It's chill once you've done the steps in order, right?
Oh.
Yeah.
But so really, you should do Z and S first, and then go to.
Yeah.
Then find.
But that's a caveat, because look at the slenderness. Sorry, look at the ZE formulas for slender. Do you see S anywhere?
No.
Because you remember that timeline thing I said?
Yeah.
So if S is here and Z is here, and ZE falls under Z for a slender case, we don't care about what fucking S is, basically. It's not involved in any of the formulas.
How are you meant to know if it's slender until you find?
Actually, you can determine the slenderness from the previous step, like before you even found Z and S. Sorry. Here, sorry, it's this little timeline thing. I've just thought of fucking compressing it all. So basically, NS, right? Lambda S is your section slenderness, right?
Yeah.
And if it falls above these two numbers, it's slender.
Then where do we get lambda SB? Oh, from that first step.
Yeah, from the step above.
So you have to do the first step. Regardless.
Yes. Yeah. And if it's in between, it's NC, which is here.
Mm-hmm.
And if it's less than SP and SY, then it's compact. Make sense?
Mm-hmm.
Okay. Yeah, there's another note here, but it's just to do with the whole like unsupported edges and stuff. It's not an important note for most cases. Just have a read of it there. But it's like a rare case. Okay, but basically, that's the formula for MS. It's ZE times FY.
Oh wow, that's easy.
But that's just the section capacity. We haven't gotten to lateral torsional buckling yet.
That's the second half. That's the second check.
Yeah.
The first check is done.
Yes.
Oh, nice. That's too easy.
Dude, are you sure that's easy? Because I don't think I'll have time to run through. Because like Sue's falling asleep, and everyone else is.
And then FY is given.
Yeah.
Yeah.
But that's not even the hard part. Hard part's the lateral torsional buckling part.
Which is what we're about to do.
Do you want to do it now, or do you want to do it?
We have 4 pages to go.
Okay. You want to go?
I'm down to finish it.
Okay.
Then it's in one video.
Yeah. Okay. So, member capacity is to do with... Oh, I put Euler buckling here. That's fucking wrong. This is lateral torsional buckling.
No risk of... If mover is fully laterally restrained...
Oh, so what full lateral restraint means is like... this is an extreme case, right? But say you have a EA, equal angle, and it's like fucking fully welded to the wall or something like that, right?
Yeah.
That's fully restrained.
It's not gonna,
So even if we have like fucking bending for like any forces going down and it's bending, it cannot. Yeah, it cannot. Basically, it means MB is equal to MS if it's fully restrained. Yeah, so then it's purely governed by its section capacity.
Okay.
Yeah. But if it's not, which is most cases, we have to do this next part, right? So MB is equal to alpha M, alpha S, and MS.
Which we found MS.
Yes. So it's very, very similar to compression in terms of how the formulas are presented. Because you remember how compression, it was like NC is equal to alpha C and S.
Yeah.
So alpha C was the slenderness ratio, reduction factor in compression. Now we have a very similar one, alpha S. That's the slenderness reduction factor for bending. But we have another thing here. This is the moment mod factor. That's a bit different.
No.
So moment mod factor can reduce your capacity, but it can also increase it.
Ooh.
So it's not just a reduction factor like the slenderness one is.
It's a modification.
It's a modification factor. It can be up to 2.5 times better, or it can be as low as fucking 0.1 or something. I don't know, whatever.
Yikes.
So this is called the moment, like the full name. Sorry, it's a moment mod factor, but the description is how well the bending moment redistributes, like the moment, I guess, for lateral torsional buckling. Okay, so we'll go over that one first, and then we'll go over the slenderness reduction factor, right? So the moment mod factor, this is the equation. So there's two ways to calculate it. One is the bending moment diagram, if you have it.
Yeah.
The best case scenario, because then it's just plug into a formula,
Is
right?
that the best case scenario?
That's the best case scenario for you, like as a fucking student calculating it.
Okay.
If you can calculate the bending moment diagram fast, or it's given to you, best case scenario. Because method 2 is fucking like a puzzle, basically.
Oh, right. So the flatter the diagram, the better.
Yeah. Oh. Wait, what are you saying?
In the method 1.
Flatter the better.
The drawing equals a higher number, which is good.
No, not necessarily. Actually, what happens is so higher alpha M is good, right?
Yeah.
We can agree on that, right? What's going on? A lower one's bad for the capacity.
Yeah.
So I'm gonna draw you 3 bending moment diagrams, and you tell me which one's the best one for the capacity. There's this one. There's this one, and there's this one. Tell me which one's the best one. So one means is the best one, 3 means is the worst one.
Mathematically.
Best four.
Wait, let me just think about something real quick. Yeah, okay, sorry, go on. So this is simply supported case, by the way, so nothing to do with cantilever. Yeah.
Yeah.
So which one's the best for alpha M? So we want alpha M to be as high as possible.
Isn't the bottom one the best?
Yes. The bottom one gives a number around 2.5.
Wow.
Okay, but the top one gives a number around 1.0, and the other one gives something in between.
Yeah, the top one's the worst one.
The top one's the worst one, and do you know how I did this racking thing?
Yeah.
That's the worst one, because when I talk about racking, I'm talking about how I was like bending that stick as if it was like a point moment on both sides, and that creates that like straight bending moment diagram, right? That flat bending moment diagram. That's the worst, because the moment has nowhere to go, basically. It has nowhere to spread out throughout the beam. But for the other 2 cases, it can go to the edges. It can redistribute, so it's the moment redistribution factor, pretty much. Does that make sense?
Yeah.
So in terms of how to actually depict this method 2 graph, because sometimes you're going to have to do it, because sometimes you have a really weird bending moment diagram and you can't easily calculate it and stuff like that. I'll cover that next week, because it's way easier to see an example of how to deal with this table, because it's literally a bunch of puzzles. So you calculate an intermediate value called beta M. Yeah.
Beta M.
Yeah, don't worry about it.
Don't worry about it?
Don't worry about it, bro. No, we'll come back to it next week, okay? Okay, slenderness reduction factor now. So we're back to reduction factor, and we're back to the one for bending specifically, right? Like before, we have LE, which is your effective length, right? It's a very similar concept, but so we're talking about the length which it can buckle, basically, like, yeah, it's buckling length. And we have a bunch of factors, right? We have KT, KL, and KR, okay? The first one, sorry, and let's just so we're on the same page. Is LE being high a good thing or a bad thing for the capacity?
A bad thing.
It's a bad thing. Yeah, because the longer it is, the more likely it is to buckle, right? Okay, so KT, it's honestly very, very minor, but depending on the restraints, it's 1, And if you have like these certain restraints, it's to do with your flanges, your webs, the distance between them, things like that. And it honestly it ends up being a number pretty close to 0. It'll be like 0.0025 or some shit like that.
Dang.
So it has a very, very minor effect. Whatever. This thing, if you calculate it wrong, obviously you're going to lose marks, but it's not the end of the fucking world because your number's going to be pretty close, right?
Yeah.
Okay, next is load height factor. And it's to do with where you're applying loads from. Okay?
Okay.
So, I know I just wrote it there, so it's a spoiler. It's worse, right? Loaded at the top flange. But why do you think it's worse for lateral torsional buckling?
Because that's where the compression, that's the weak point. It's at the top.
It's not really that, it's the weak point.
It's more tilted.
It's like if I drag this chair down from the middle, it's not really gonna wobble like left and right. But if I drag it down from the top,
Oh my goodness.
it has
The
this
moment
essence.
is
Yeah. It's like because we care about the twist, right? We care about that like. So it has a bigger lever arm basically. If I push it down from the top, it causes like an eccentricity and pushes it off to the side, right? Whereas the left case is called the shear center. So let's think about this in real life, right? Like what kind of loads will be applied to the shear center?
Jet columns.
Sorry, this is just for a beam.
Dirt.
Self-weight.
Self-weight.
The weight of it is going to be loaded from the middle because it's the
Real.
center of gravity, right?
What about dirt?
What?
Like dirt, because it's from like all around.
We don't really have a beam in the dirt.
Oh.
Yeah, it's just different because these are suspended beams in the air, right?
What about air? Wind load.
Wind load.
Gravity load.
Wind load is probably more flange because if you have wind that's pushing down or sucking up, it's going to be loaded at the flange.
Oh, so that's bad.
Yeah.
But this is for where?
Now shear center.
Yeah, but top flange loading. What's an example of top flange loading?
Of weight.
If you
Live
put something on top of it,
Live
basically, right?
load.
Yeah, live load, anything, right? So most of the time, it's actually the worst case scenario.
Ah, fuck.
Yeah.
No.
And you know how much worse it is?
This is 2 times worse.
It's either 1.4 times worse or 2 times worse. But it depends, right? So within segment is like if you have a uniformly distributed load like that, it's loaded within the segment because the segment is the entire beam. If you have a segment end, that means like it's loaded there or something.
Oh.
It's at the end, right?
Oh, that's
So it's like a
worse.
point load or some shit.
That's bad.
Yeah, but actually no, it's honestly better for most of these cases. For top flange, right? The thing is, the worst one is cantilever. Because cantilever is unrestrained at one end, right? And so you have this 2 times loading if it's loaded at the flange and it's cantilever.
Yikes.
So then the effective length is fucking doubled.
Oh, that
It's
is
like a big
so
effect.
bad.
Yeah. Okay, and then lateral rotation restraint factor. I don't know why I didn't highlight this in my notes, but for these ones, for FF and like all that shit, just consider it as none. That's worst case scenario.
What?
And the unrestrained ones, the cantilever is also 1. So basically that one's always 1. Because these ones are like, they give it additional strength, like it reduces the effective length, but we just take the conservative approach. This is what Hamid said. I don't know what Brian says, but I guarantee it's
No, Brian's just the same.
just keep it as 1.
Okay.
Yeah. That's about it's about lateral. There's a rotational restraints at the ends. How much it restrains like rotation, but whatever. Just pretend that it's not restrained at the ends. We haven't even gotten to this. Oh my days. Do you remember when I said last week this is the hardest topic?
No, you're kidding.
I'm not fucking kidding, bro.
You're kidding, bro. This is easy.
Is it easy?
Yeah.
Alright, sure thing. Okay. But a reference buckling moment. Do you remember how I said all the way back in like the second week, I showed you that weird formula?
Yeah.
Euler's buckling formula?
Yeah.
I was like, oh, don't worry about it. It's not this course. It's basically in this course because because it's in this formula, right? But they modified it a bit to include like they like so. But this includes the Euler buckling part and the like rotational part, and that's what lateral torsional buckling is.
Wow.
So the part that should look quite familiar is this. That should look very.
Yeah.
That's
the buckling formula.
That's your P. Fuck, what do they call it? Critical, I think. That's your critical
load.
your critical load, right? So that's the load, and then you multiply by this shit, and that's the. There's a difference between twisting and warping. I forgot it, but this one's to do with but between torsion and warping. This is like the torsion part, and this part's the warping part. So it's got this part that's like IW or something.
Okay.
Anyway, point is you have to consider both for an I-beam, right? For your equal angles, unequal angles, hollow sections, like circular hollow sections, square hollow sections, we don't have to consider the warping part. That's kind of what I was saying. Oh, actually, no, it's a bad way to put it because this is supposed to give it more strength. It's just this value for J is going to be really high, this torsional resistance for these
and that's
shapes.
in one still.
Yes. If it's a custom... if it's a custom shape, it's not.
How you find it?
They'll probably give it to you because the way you calculate that varies so much from shape to shape.
So you're probably not going to need to know.
I have an example next week on how to do it for a rectangular hollow section. How to calculate J.
My, and IW as well.
IW. The thing is, in my question, it's a rectangular hollow section, so it doesn't need IW. IW has another way to calculate it. I think it's in like the appendix of the standards. There's a simplified method because the full method is fucking ridiculously aids to understand. The standards has like a simplified method to calculate IW. No, but I don't think you understand, Lockie, because the assignment that Brian did for last year's cohort for the flexure part was a monosymmetric I section, custom shape.
So like the bottom one.
The bottom formula. Do you see how fucking AIDS that is? And you have to custom figure out J and IW based on the appendix of the standards.
Oh, I don't give it to you.
No.
Oh my goodness.
It's the most AIDS fucking thing you can possibly imagine. Just to calculate like fucking reference buckling moment, right?
Is
and I just gave
allowed to be said anymore? That discrimination.
AIDS.
Yeah. It's like a disease. You know?
Yeah.
Like I said, that's like me saying that's so schizo, you know?
That's actually a very good point you raised. Alright, let's move on.
I'm serious, bro. I'm gonna cancel you, bro. I'm cancelling you live on YouTube.
Okay. AS is what we were after the whole time, right?
Yeah.
That's
alpha.
Oh, sorry. Yeah, you're right. Alpha S is what we were after. Because we already found alpha M, right?
Yeah.
So now MS was what we found when we found the section capacity, and then MO is the reference buckling capacity, right?
Yeah.
And that's that, and then you check that, and it's all good. Okay, but you ready for this shit?
I'm ready.
So imagine you have that beam again, right? Actually, let's just do a simple one. So we have a simply supported beam. Okay.
Yeah.
This one's fully restrained on both ends. And we have two lateral restraints in the middle, right? So little like EAs restraining not the critical flange, which means it's L. And then these ones are fully restrained out of plane, something like that, right? That's kind of like how the questions have been presented to you.
Yeah.
And then you have your like fucking loading, so the UDL and stuff like that. Great. Question is, because I haven't fully talked about segments and subsegments, right? Where do you think the segment starts and ends? Let's call this A, B, C, D.
Between the lateral supports.
Lateral supports? You're talking about these?
Or between all the supports.
Between, yeah,
One, two,
the
three,
supports. So these are fully restrained.
Yeah.
Right. So A to D is a segment.
Oh, actually.
That's a segment. A to D is a segment.
Okay.
So we call that segment AD. Okay, what about A to B? What do we call that? Call that a subsegment. That's a subsegment. AB. B to C is a subsegment, C to D is a subsegment. But like because of, let's just say because of symmetry, we don't need to consider C to D.
Okay.
So we have to consider segment AD, subsegment AB, subsegment BC.
What about A to C?
A to C?
No.
That doesn't.
included.
That's nothing anymore because a subsegment is between lateral restraints.
Oh.
Yeah, and a full segment's between actual restraints, like
Okay.
full like vertical restraints,
Okay.
right? Thing is, you ready? We're not even.
Yeah.
This wasn't even my point, right?
Okay.
Alpha M is calculated per segment.
Real.
Yeah.
Yeah.
So alpha M
That's great.
for this whole thing is going to be alpha M. And what about we got for alpha M, right?
Yeah. Oh, so it's constant. It's the same.
For the whole segment.
Oh shit, bro.
Alpha S, guess what? Is per subsegment.
Ah. Nah, that's chill, bro. That's vibes, bro.
So this will be alpha S1. This will be alpha S2, or like I wouldn't call them 1, 2. I'll just call them alpha S AB, alpha S BC. But then this would be for the whole thing alpha M.
Bro, alpha M.
But this is a simply supported case. Imagine you have fucking like continuous beam with like multiple things, right? And then you have fucking multiple lateral supports.
Right. So
You see
alpha
how-
B is kind of Chad.
Alpha B doesn't exist. You talking about alpha S or alpha?
Alpha M.
Yeah.
Alpha M.
Alpha M is so
original.
between here and here you'd have a certain
Day
alpha
one,
M,
bro.
and here you have a different value for alpha M, and here you have a different value for alpha M. But you could potentially have different alpha S values for each of these things, right? But that's all just to calculate MB, and we have to find the worst one to compare it to the worst bending moment, right? Can you imagine the fucking bending moment diagram on these?
So you're praying there's a bending moment diagram.
No, you calculate it as your first step, pretty much, unless it's given to you.
I thought a bending moment diagram you can skip everything.
What?
You can skip all the steps if you have a bending moment diagram.
No, you probably have to calculate the bending
Oh
moment
yeah,
as a
you can
first step.
skip AM. Oh my goodness.
Yeah.
With the
So here's the full guide for flexural design. That's just everything I ran through today. Is this?
Shit.
Go.
Shit, cuz.
Goes to America once. But yeah, makes sense.
Yeah, for real, my G.
And then do you see this part that's purple in the diagram? That just says, because you can't read it, find ZE to calculate MS, right? And here underneath I've expanded on this as in it's part of the lecture slides, but they have the exact step-by-step of what to do.
That's just so crazy.
Okay, any questions?
Can you explain the whole thing again?
Okay, let's go from the top.
Here you go.
Yep. Alright, I'll let you guys go. That one was actually a 90-minute, yeah.